Okay. Bueno, Daniela, puedes empezar a hablar.
Buenas tardes a todos. Soy la doctora Daniela López de Luis, investigadora en sistemas inteligentes. Les doy la bienvenida. Es un placer para mí darles una breve introducción y presentarles la conferencia del doctor Witold Pedrycz. Pertenece al Departamento de Ingeniería Eléctrica y Computación de la Universidad de Alberta, en Canadá. Intentaré contextualizar la temática que están por escuchar, que es muy interesante. Para los que no conocen al doctor Pedrycz, les comento que es una destacada figura del IEEE que trabaja en áreas como teoría de conjuntos difusos, aprendizaje automático, clasificación de patrones, análisis de datos, extracción de características, minería de datos, redes neuronales, análisis de regresión, computación evolutiva, series de tiempo, redes neuronales difusas, optimización Pareto, y podría seguir con otras temáticas que el pródigo Witold ha estudiado y desarrollado a lo largo de su carrera hasta la actualidad. Por supuesto que entre estos temas está la computación granular o, como lo venimos divulgando, la Granular Computing. Las actividades y los ámbitos de interés de Witold caen bajo el paraguas de los fundamentos de la inteligencia computacional, puesto que él entiende que las mismas comprenden tecnologías claves tales como los conjuntos difusos, la neurocomputación, algoritmos genéticos y las técnicas de evolución genética. Encuentra atractivas estas áreas porque se enraizan en la construcción de sistemas híbridos que exhiben diferentes niveles de aprendizaje, combinan la representación explícita y tienen mucho poder en el manejo de conocimientos complejos. Con estas técnicas no solo puede hacer un aprendizaje automático, también es capaz de trabajar y dominar las actividades con niveles de cierto tipo de incertidumbre. Considerando que este es el marco conceptual en el cual trabaja Witold, por supuesto que hay distintas vertientes y bien definidas en las cuales específicamente está trabajando. Entre ellas están ingeniería de software, modelos de sistemas y descubrimiento de conocimiento, arquitecturas reconfigurables y evolutivas y reconocimiento de patrones. De todos estos, la charla de hoy se encuadra en lo que nosotros denominamos modelos de sistemas y descubrimiento de conocimiento. Aquí el interés importante es el manejo de un modelo que explote el potencial de los conjuntos difusos, teniendo como objetivo primario un desarrollo orientado al usuario. Para esto debe estudiar la representación de datos heterogéneos con un nivel de granularidad variable, modelos lingüísticos basados en relaciones y patrones de datos con modelos jerárquicos o distributivos. Entendemos por granularidad en este contexto a un nivel de abstracción o complejidad determinado. El modelo difuso en estas instancias se convierte en una herramienta central para la mayoría de las aplicaciones que llegan a incluir los tradicionales controladores difusos. En este área, que Witold se centra específicamente en sus investigaciones, y es por eso que le hemos pedido que nos hable en esta disertación de hoy. Si bien Witold les va a comentar sobre lo que es Granular Computing, me permito adelantarles que es un paradigma informático emergente de procesamiento de información. Se centra en entidades de información complejas llamadas gránulos de información, que surgen en el proceso de abstracción de datos y derivación del conocimiento a partir de información o datos. En términos generales, los gránulos de información son colecciones de entidades que normalmente se originan en el nivel numérico y están organizadas juntas debido a su similitud, su adyacencia funcional o física, la coherencia o cuestiones de afinidad específicas. En la actualidad, fomenta un acercamiento a los datos que reconoce y explota el conocimiento presente en los datos y considerando varios niveles de resolución o de escalas. En este sentido, engloba todos los métodos que aportan flexibilidad y adaptabilidad para poder hacer resolución de un cierto tipo de problema. La computación granular no es un algoritmo o un proceso específico. Esto es, no existe un método en particular que se llame computación granular. Es más bien un enfoque para poder observar datos y que reconoce cómo diferentes e interesantes regularidades de los datos pueden aparecer en diferentes niveles de granularidad. Al igual que diferentes características se vuelven sobresalientes en imágenes de satélite cuando uno hace mayor o menor tipo de resolución. En una imagen satelital de baja resolución, por ejemplo, uno podría notar patrones de nubes que sean interesantes y que representen ciclones u otros fenómenos meteorológicos a gran escala. Mientras que en una imagen por ahí de mayor resolución, uno pierde estos fenómenos que son atmosféricos a gran escala, pero en su lugar nota fenómenos de menor escala que antes no veía. En general, lo mismo ocurre con todos los datos. En diferentes resoluciones o granularidades surgen diferentes características y relaciones. El objetivo de la computación granular es interactuar y intentar aprovechar este hecho, ¿sí? Para poder diseñar sistemas de razonamiento y de aprendizaje automáticos que sean más efectivos. Hay varios tipos de granularidad que se encuentran a menudo en la minería de datos, que es una de las áreas, y el aprendizaje automático, controladores, sistemas de control de calidad. ¿Qué cosas permite hacer este tipo de modelo granular? Bueno, hay una serie de aplicaciones de interés en la industria, como las que voy a detallar a continuación. Entre ellas el análisis de controladores en cuanto a su robustez y tolerancia a fallos, diseño de controladores basados en modelos, estructuras de decisión y de control híbrida y jerárquica, arquitecturas dedicadas, obvio de hardware, ¿no?, que sean más veloces, específicamente para redes neuronales, aplicaciones a redes de cajeros automáticos, bueno, y muchas otras. No quiero hacerles esperar más y por eso ahora los dejo con el disertante. Muchas gracias.
Good morning, everybody. I'd like to welcome you at my talk from data and concept perspective of granular computing. First of all, I'd like to really congratulate the organizers of the conference for bringing these very important and very broad topics to the attention of the research community. And I'm sure that this is a very successful event. So my talk is really about ideas of information granules as a certain vehicle that brings us closer to the concept of data understanding, to the concept of modeling of complex systems, to the ideas that are very much visible today, namely aspects of interpretability and explainability. So today's agenda really arises around a couple of items. First of all, I'd like to look at these ideas of interpretability that seem to be very dominant on today's landscape of information technology, and showing that the ideas of interpretability can be nicely and efficiently processed using information granules. I would like to touch upon different ways in which you can move from data to information granulars, and then concentrate on ideas of rule-based computing and information granularity. Well, let me start from an observation that I suppose is quite visible today, that essentially when artificial intelligence became very popular in the recent years, there was also the question of interpretability of the resulting constructs. And this was raised from the perspective of human centricity. And from this point of view, we had this some legal sort of requirements that when you have AI construct, then the user has to have the right of explanation. And also because the way how different sort of models of AI have been constructed just recently, and we observed these aspects of possible adversarial samples, then this particular point also had to be addressed. What do we mean by interpretability and explainability? Well, interpretability is really about forming results in the way that they are easily understood by the user, and the user can comprehend the results, can take some action on their basis. So in other words, there should be some actionable findings. So naturally, interpretability has to be in the realm of activities, in the realm in which people sort of perceive the world. We do not think in terms of numbers, we think in terms of more abstract concepts. So for instance, terms like low value of sales, high likelihood of sort of medium temperature, those are pieces of knowledge that communicated to us convey some useful and actionable finding. But when it comes to explainability, it is very much linked to interpretability, but it mostly focuses on ideas that you should be at position to produce knowledge about models and how the model perform on the basis, the model that have been built on the basis of numeric data, or predominantly numeric data. So essentially, we have to possess models that are transparent. Obviously, when you look at the current plethora of models that are very much advanced, we can see that some of them are very far from this sort of target. They are regarded as black boxes, and some of them are sort of more suitable, and under this category, you can encounter rule-based models. So essentially, you ask a number of those very detailed questions that contribute to this entire concept of explainability. So you have to talk about what-if analysis. You should be able to trace the entire reasoning process. You have to be at position to talk why a particular model produced a given prediction, and what if some other condition happened, what could have happened to the prediction. And in this sense, we can see a very interesting synergy that arises, because on the one hand, if you look at modeling environments, they are equipped with an entire spectrum of different tools, different optimization frameworks, and they are applied to a vast number of applications. But most of them are based on numeric variables, and they are based on numeric data. And well, you have masses of data, and essentially you can proceed with all this technique of data analytics and come up with some sort of meaningful results. But if you look at this kind of other part, that I think I was talking about explainable artificial intelligence, and you can find that essentially those are based on symbolic processing. So the question is, where you have symbols, where are they coming from? How well are they grounded in a particular environment that you model, or the particular problem that you are sort of talking about? And this entire bridge that forms this, that sort of creates linkage between these two areas, is just realized through information granulars and in general granular computing. Well, why it's so important? Because essentially we have to move from data to some abstract descriptors of data that are interpretable. So you have to realize a certain process of abstraction. And I suppose we can see this everywhere. You are seeing masses of data, but at the end of the day, you are really coming up with some descriptions that are very much concise, but they are very much loaded with just a sort of knowledge that you acquired. So here are just some examples. Here's another example. Looking at the signal, you really are not looking at individual data points, but you are building a piece of knowledge that is reflective of this signal. So not signal. So that in the sense, we have to really admit that we are building on the basis of data, but we have to come up with a certain representation of our findings. And this is just the process of abstraction. And this is the process where you use information granulars. Because all these highlighted sort of terms here are nothing but some sort of concepts that can be conveniently realized by information granular. Here's another example. You have a lot of data, but you are coming up with a certain summarization of data. So summarization involves a number of those more abstract entities. How are these entities sort of formed, and what are their characteristics? Well, there are at least two of them that are very important. It means when you talk about a certain level of abstraction, it comes with this idea of grounding within the framework of some data, but also it comes with some concept of specificity. Just not getting into any mathematical details, let's try to look at those examples. So I'm talking about a piece of knowledge that concerns a temperature that has been formed, or the description of temperature that is formed on the basis of data. So notice that if you start moving from the bottom to the upper portion, then essentially those pieces of knowledge are more abstract. Well, we can see that essentially they start covering more data. But at the same time, these pieces of knowledge, if you go in the opposite direction, they are more specific. Like this is a very specific piece of knowledge. And you can look at these intervals, and they have satisfied this inclusion relationship. So they become less and less specific. So it's noticeable that when you're talking about level of abstraction, behind an information granular that you start forming, there is this concept of support provided by data to sort of get to produce this information granular, but also a level of specificity. Obviously, the question is there any kind of ideal solution? Well, it depends on the problem. So in other words, the level of abstraction could be problem dependent, could be user dependent. The same data could be perceived at a different level of abstractions. You are not really maybe looking at any sort of details because they are probably not relevant. They are not as sort of central to the problem you are about to solve. And what is very important is essentially that this level of abstraction allows us to look at the problem in a more holistic way and not being buried in details, which in sort of at the very end do not allow us to understand the problem. Here's this very well-known sort of idea of blind man and an elephant. If you're getting too close, you are only observing a small, tiny fraction of the sort of entire phenomenon, and you can not be able to understand what this phenomenon is. So information granularity is a very important vehicle, a very important concept to realize information granulars. Obviously, when you look at information granulars and granular computing in general, we can observe that there is really a large spectrum of formal settings. There, here you have some of them, probably fuzzy sets, probabilities, rough sets are quite visible, especially in the context of computational intelligence. You have some sort of interval analysis. Each of these formalisms has its own underlying philosophical and algorithmic foundations, and they are reflective of the way how you sort of build your abstraction of the problem. Obviously, the fundamental question that arises is about design of information granulars. Where are they coming from? I think one has to be very much clear on this, that information granulars are just examples how you ground some abstract entities. So in other words, information granulars have to be built on a basis of some experimental data. The information granulars are not coming from a vacuum. They are not really groundless. They have to reflect data that you have. So that's something that you do in data analytics. You move from data to information granulars. So what are the existing techniques? Well, there are a lot of them. I suppose one that is very much established, and I think it has been established for and has been developed for a number of decades, is concerned with clustering techniques. Because clustering is really, in a nutshell, it's a way of building, of revealing structure in the data. And then you have a lot of methods in terms of philosophy, in terms of objective functions, and you have just the results that are mainly produced for numeric or categorical data. It is worth emphasizing that in virtue of the concept of closeness, that is the cornerstone of clustering techniques, this concept is also the same as is behind information granulars. So in other words, in information granulars, you talk about entities that are put together because they have something in common. In clustering, you have the same situation. You put some elements together because they are close to each other in some particular sense. In clustering techniques, we sort of form a structure that has at least two clusters. There is another approach that is probably far simpler than the clustering technique. I think this approach can work together, but I think it could be a standalone technology here. And this is known as the principle of justifiable granularity. What is the main idea? Well, the main idea is that you have just data and you are trying to build a single information granular. I mentioned that in clustering technique, you have to form at least two clusters, okay? But here you have data and you want to describe the data by a single information granular. So then principle of justifiable granularity is just a suitable way to do this entire process. Information granular that are formed on the basis of this principle are, in a nutshell, formed by relying on two very simple principles that I already mentioned. Because if you have an information granular, its two key features are the coverage, so how strongly you are justified by the data, but also how specific your information granular is, namely, how much semantic soundness this information granular conveys. And having said that, you can formulate this concept of coverage and specificity in a more sort of formal way. So coverage would be, as everybody could envision, related to the idea of containment of data within the bounds of information granular. So for instance, if you have data and you have just form a certain sort of spherical shape, then you really consider this to be information granular. And if you start increasing the radius, then this information granular is going to be larger. So it starts covering more data, the coverage increases. But at the same time, if you regard specificity as being a decreasing function of the size of the information granular, in our case, it's just the radius, then obviously then specificity declines. So coverage increases, specificity decreases. And if you want to reach a certain compromise, then you probably can try to maximize a product of coverage and specificity by taking some value of this radius. So once you carry out this construct, you really get the data being described by the information granular, and information granular, in general speaking, can have just its sort of geometric signature. So that means that the location of the center and the radius. Please notice that the geometry of information granular is dependent upon the distance function. So what I'm showing here is just evidently a Euclidean distance function. But if you consider Chebyshev distance, then your information granular becomes, generally speaking, a hypercube. And there is also some content signature. So in other words, the content of the information granular, what it includes in terms of some features that are concerned with the problem. From the perspective of machine learning, you can consider that information granulars can be viewed as generative models or discriminative models. So as usual, generative models are aimed at the description of the structure of the data, whereas discriminative model is really considering information granulars as those building blocks that form classifiers, predictors, association models, and alike. So if you are talking about classification problem, notice that this information granular has its geometric content, but also it has a classification content that really tells you about the probability of occurrence of different classes within the bounds of this information granular. But also you can think about information granular in a sort of more general setting as, for instance, a certain rule in the rule-based model. So in this case, you have geometry, but then you have an information content that is far richer than before because you are talking about both condition and conclusion part that are described by information granulars. So these information granulars can be sort of described, can be characterized by some measures such as coverage and specificity. Then, as you remember, in rule-based models, we have to talk about some matching procedure. So it has to have this kind of communication mechanism, talking about the invoking of a certain this particular information granular, and the sort of way of interacting with the external world in terms of some encoding or decoding mechanism. Interestingly enough, if you look at information granulars positioned within the bounds of any particular rule, you can find that there is a very sort of convincing illustration, because essentially when you are talking about a rule-based model where both condition part and conclusion part are just information granulars, in particular fuzzy sets, as I think this been a very popular research area. So the quality of the rule can be really sort of a sign, or could be really associated with the nature of these information granulars and with the way how they are related. Here what this graph illustrates is just a position of the rules with regard to the specificity of their condition and specificity of their conclusion. Remember, the specificity is about really the level of abstraction. So in other words, a very specific information granular is the granular which size is very small. So for instance, you can see a situation like this. So you have just AI that has a very high specificity, but its conclusion part has very low specificity, BI. So this is the situation that is localized in this coordinates at this point. You have some other combinations. And based on the analysis of the specificity of information granulars forming condition and conclusions part, you can essentially easily assess the quality, the relevance of the rule. Because the rule that is ideal and that is of high relevance is the rule whose condition part is very non-specific, low specificity, and whose conclusion part is very specific. Because in practice, what this means is that this rule becomes applicable to a large situations, to a large number of inputs. And yet, at the same time, the conclusion is very specific. On the other hand, the rule that I sort of presented here is the rule whose relevance is very questionable, because you have a very specific condition. So this rule can only apply to a small spectrum of inputs in the input space. However, the conclusion is very non-specific. So in this sense, by bringing information granularity, the concept of information granularity, to rule-based models, we can sort of assess the quality of the rules from the perspective of their interpretability. Now, I was talking about explainability, and I was talking about interpretability. One has to emphasize very strongly that these features are very well sort of present in rule-based computing. And if these rule-based computing are inherently associated with information granulars, then you can really get a very good, very instructive insight into interpretability and explainability. For instance, if you are talking about explainability, you can look at rules and you can sort of identify which rule has been fired to the highest possible extent. When you are talking about interpretability, well, the rules can be interpreted quite easily because you have a logic structure, but also you can enhance this interpretability, in particular if you have highly dimensional rules. The rules, we have a large number of conclusions, by bringing the concept of so-called linguistic approximation. So in other words, the ideas that have been around in fuzzy sets for a long time. So if you have a rule that has a number of these conditions, then you can carry out their summarization to arrive at statement that most of these inputs are, for instance, low. So in other words, you are trying to compress the rule from the perspective to its easier summarization. So please notice that essentially what we are really looking at these ideas, or looking at the challenges that we have in system modeling, then we have in data analytics. And those are just the ongoing challenges that you can sort of position them and rectify problems by bringing this fundamental concept of information granulars. Abstraction levels, yes, you can easily adjust these abstraction levels by bringing information granulars at a certain level of specificity. Rule-based models exhibit modularity. Then you have just a kind of interpretability and explainability, because those rule-based models are typically sort of logic-based. And also you can offer some granular evaluation of performance, well, because you can quantify the conclusion in terms of their, for instance, likelihood. But having said that, we have to be very much aware of the fact that today, when we have highly dimensional data, this problem is going to become very much apparent and very much visible and very much challenging. Because if you have highly dimensional data, well, if you proceed with rule-based models instantaneously, then this dimensionality issue is not going to disappear. And I think this is going to be present in the rules that might have high dimensional conclusion space. So what is the solution? Well, the solution is well known in terms of this dimensionality reduction. However, if you do dimensionality reduction in the standard way, such as using a principal component analysis or linear discriminant functions, then you have a problem that this reduced space starts losing its interpretability. So what is essentially a possibility to resolve this problem? Well, you have to really think about a reduction of dimensionality, but by some transformation that are transparent. So I mean by a logic transformation. And here you can sort of consider some of these concepts that come from sort of existing studies, and they are recasted, they are reformulated in the language of information granulars. So you can talk about, autoencoders, you can talk about logic autoencoders, you talk about this very well-known idea of non-negative matrix factorization. Here you can engage a relational calculus of information granulars, and you can talk about relational factorization. So then in this reduced space that is completed through logic transformation, you can form the rules, and then obviously you can proceed with conclusion and offer some sort of performance associated with the results. There is another one of these sort of possibilities here is essentially just to make sure that rather than working with the original space that is highly dimensional, you can go through this reduction by some logic expressions. So essentially here it's not a collection of information granulars in the individual space, but rather a logic expression formulated in the original space. I think my time is almost up, so I would like to offer some concluding comments. My primary intent of today's talk was to really highlight this idea of information granulars and granular computing as a vehicle to deliver, to construct, and to enhance models that are both interpretable and explainable. And in particular scenario here, I sort of emphasize the role of rule-based architectures that have been around for a long time, but nowadays there is a kind of another wave of interest in these techniques in light of this, driving force towards interpretable systems. So I would like to thank you very much for your attention, and I'll be happy to I don't think, answer any questions, but I suppose you can contact me sort of offline and just after the conference, send me an email. I'll be happy to provide you with more additional material and more detailed information. So again, thank you very much and wishing you a very successful conference. Thank you.
Bueno, damos las gracias al doctor Witold Pedrycz. Como hemos visto, tenemos esta forma de pensar que replantea todos los conceptos que ya conocemos en el área de procesamiento de datos y minería de datos, desde procesamiento de lenguaje hasta controladores. Y bueno, como dijo el propio doctor Pedrycz, pueden contactarlo vía email por cualquier comentario o consulta al email que él mismo puso en su presentación. Lo voy a recalcar, es wpedrycz, ¿sí? Es el apellido con el nombre, la letra del nombre con el apellido, @u de universidad, alberta.ca. Y en caso en que ustedes deseen que los contactemos nosotros, podrán hacerlo a mi casilla personal, que es daniela-ldl@ieee.org. Por su tiempo, muchas gracias.